Okay, why don't I begin? So I'd like to start by thanking the organizers, Eric Sharp, Ron Donaghy, the rest of you for initiating what I think will be an important series of meetings and setting a high bar for us to follow in terms of the quality of the organization and the quality of the talks. And it's also, I think, symbolic in the representing the coming of age of this subcommunity of string math. And so it's interesting to see, in some sense we're at least mapping out some boundaries of what this field consists of. And so I chose a talk to try to expand the boundary in another direction, which is represented. I know Kevin Costello is speaking about these types of questions, but not many others. And I'll try to explain why I think this is an appropriate topic for all of us to consider. So, okay, so obviously, there's a question which certainly belongs in a formal physics math interface. How can we make mathematically precise definitions of quantum field theory and string theory? And it's not a new question, and many people have been working on it since before string theory and before much of what we now know about quantum field theory. And there's a variety of approaches, and it would be hard to survey them all in one talk. I'm going to just concentrate on a couple of things, such as conformal field theory, which I've worked on, constructive quantum field theory as one of the more established ones. But of course, the first point to make is that it's fascinating from any point of view that you can have so many points of view on one subject that they come at it from different ways. So the goals of the talk, well, examine that question. What is mathematical precision? I'm a physicist. What do I have to? Why am I interested in talking about mathematical precision? Well, I think there are questions that we as physicists are kind of stuck on because we have not gone very far in that direction. There are questions which, again, barely existed back when this field was more popular, say back in the 70s. And now that we know more about quantum field theory, we can come back and try to, we ask these questions and we realize that those issues, which I'll explain, are relevant to them. Okay, so just a very brief, let's recall, some of us are mathematicians and some of us are physicists. We're studying this common field, this interface, and nevertheless, we see ourselves as at least two parts of this subcommunity, and in most respects, two members of two different communities. And how did that come about? Certainly wasn't always true. And of course, a very basic comment is that back in the 18th century, say, the community was incredibly tiny, and one person could hope to follow all of it. And that certainly no longer true. And if you look at the history, it really changed over 100 years ago. And already then, it was hard for one person to follow all the important developments in this broad area of physics, mathematics, ... And then, of course, there are much more specific developments you can point at, which both require a good deal of training and thought to really appreciate, and which tend to bring people in a certain direction, perhaps at the expense of other directions. And so obviously the development of mathematical rigor in this period of the mid to late 19th century is key development in mathematics. And as a physicist, some of my teachers were mathematicians and followed this, and some of them did not. And for whatever reason, I didn't myself internalize all of this. So that's a concrete example, which I'm sure many of you can sympathize. Okay, so then why is mathematical rigor at all good? Well, I'll come back to that. But it goes along hand in hand with this acceptance of non-constructive methods to say that you can prove that something exists in principle without even saying anything about how you would ever find that thing that you proved exists. And of course, that's an extreme case, but definitely we're all used to this type of argument. And once you regard this as important or as good as a constructive technique, this again changes your point of view, and you have to be much more confident now in the quality of your arguments, since you don't have the actual object at hand that you're proving exists. And then conversely, there really are many examples I don't want to list of techniques which were developed really much more for the purposes of physics, engineering, ... which don't have quite the same appeal to mathematicians. And you may see, we can decide as we go through the talk to what extent things I'm talking about fall into that category. But again, it's a real thing, which means that this is inevitable. This I think division into two communities, and then we as the string math community should keep that in mind. So of course, this trend grew over the years, and there are these famous quotes from the sort of most the dark ages of math physics interaction. This is one of my favorites that I read as a grad student. And then this is another very famous one by Freeman Dyson in a address to the AMS, where he in fact goes on to propose constructing or showing mathematically that quantum field theories exist as an important problem. And so, well, things have improved since then. And so we have a number, because string math is also not at all unique in being some type of mathematical physics in which mathematicians and physicists study common structures and have overcome the language barriers, and there are sociological barriers, and the various of these more superficial barriers, and can start to look at, well, here are these two groups of people with somewhat different training talking and writing about the same thing, and it's always interesting to look at an actual pair of papers about the same thing. And again, one could probably give a whole talk about this, but as you all have experienced, the math paper was a very specific mathematical style which evolved over the years, which has a lot of advantages in terms of precision, definition, theorem, proof, and in terms of explication, and that a very typical math paper will explain in the first section what it is they are working on, what problem they claim to solve, the rough overview of how they do it, and then get into the details. Whereas the typical physics paper, as you all know, will say, well, back in 1987, famous person X proposed this, and then there was this and that development, references 1 through 100, and now we're working on this part of it. And then that has its own value, but it's not really as clear to the outsider. And it then goes on, again, to be, in this term I've heard from mathematicians, discursive, and tell the story about, here are these different examples we can work out in physics. We go 1, 2, 3, infinity. And then infinity is this very interesting conjecture, which often in our subfield turns out to be correct. So that obviously there's value to that. So, okay, so I certainly can't really criticize that, but there is this other approach of trying to make physical definitions and claims rigorous. And of course, this is the traditional definition of mathematical precision. People do prove theorems. They get them published in math journals. They get jobs based on this and so forth. And again, not something one can really criticize, but as a physicist, I'm going to not actually emphasize that point of it. Okay, and in fact, you can hear a number of mathematicians say that, in fact, that as a goal, that's not the central goal. That's not how they would, define mathematics, and rather they would say that, there are these structures out there, perhaps created by us, perhaps Platonic, but in any case, the purpose of the mathematician is to understand these structures, to communicate this understanding, and the proof is only one and perhaps not the most important element in that. And a number of people, such as Thurston have written eloquently, making on that point of view. So okay, so having right from the start just said, well, I want these, I'm going to talk about these rigorous foundations, but I'm not actually going to care that much whether they're rigorous. You may think that this is a again futile exercise, but again there's a point I'm trying to get across and understand, and so let's continue. So we certainly have so what are foundations? Again, it's a word I'm not going to try to define or explain in great detail, but we tend to know foundations when we see them, and they are the things that appear in textbooks when they're very well developed, and then there are many such topics in quantum field theory already. Certainly all the textbooks emphasize perturbation theory around free fields, perturbative renormalization theory. These are really the heart of the subject. There are axiomatic statements saying what we mean by a quantum field theory, what properties it really should have to be counted as a quantum field theory. That's certainly foundational. There's a huge amount of structure in respecting symmetries, gauge invariance, more subtle aspects of the theory, and these are all foundational. And it's no coincidence that there has been rigorous work done on all of these topics. And so there are other foundational topics which I'll get to. Now, again, one could do these things rigorously or not, and it might or might not help somebody understand. It might help a mathematician understand because he's used to that. It might help a physicist understand it for other reasons. But again, the mathematical treatments tend to emphasize slightly different points and to ask questions that often either don't occur to the physicist or are just treated very superficially in a page. And so, for example, one well-known question here is, what does the choice of field variables, in a functional integral or some other formulation mean? Surely it's not a fundamental aspect of the theory, and you can make field redefinitions, take fields which are local functionals of the fields you started with, and in some way get the same theory. And that's certainly discussed in physics treatments, and one has LSD theorems regarding the S matrix and other sorts of theorems about field redefinitions. But it's sort of a side point. It's something you should keep in mind. Whereas some of the mathematical treatments make this really very central to say that, well, this is geometry. The whole point of geometry is that the coordinates are not the central conceptual thing. They're just a tool to use to describe this structure, which somehow could exist without coordinates, even though we have to use coordinates to work with it. And so that's certainly a very different point of view than just, here are field redefinitions. Let's talk about them for a page. And there's something to learn from that point of view, especially as a string theorist. Okay, again, another obvious point. How does one deal with these infinite number of degrees of freedom? We all have to cope with this. And there are a lot of mathematical tools which can be useful both in terms of proving and in terms of making the points clear. Okay, now of course there are many topics for which the communities to some extent started out closer together. The physicists started out talking to the mathematicians. They're really pretty good already from any point of view I'm talking about here. And many of the topics we discuss in these conferences are like that. Certainly solitons, instantons, especially things that you really can formulate either classically or in terms of one loop quantum physics. These are things with good mathematical foundations, and there's not that same level of difficulty. So it's not a universal problem, but there are various foundational topics which I, as a physicist, would like to be able to call on, which aren't as well developed, in my opinion, as what I discussed. And so one very basic example, I'll say more about what I mean by all these things, is that there's a huge discussion, thousands of papers, many textbooks on perturbation theory around the free field theory, the free boson, the free fermion. And there's very little about perturbation theory around other solvable models, conformal field theories, or models that you might imagine solving other ways. And this would be a very valuable tool. And in some ways it's similar, but it's obviously, for reasons that I'll get to, more complicated. And it's not that there aren't papers. Very periodically, every year, one can see maybe 10 or 20 papers on this subject. The problem is that none of them really quite gets to the bottom of it. Nobody developed a formalism that you can go out to all orders and so forth. And so that's a foundational topic which, again, it's out there. It deserves to be developed. I don't think a very good job was done yet. Exact normalization group is another of these. The conformal bootstrap, again, I'll talk more about it. Very good in 2 dimensions, c less than 1, not terribly well developed, and there's a few other cases, but again, this is something foundational which we ought to understand better. Large N, there's a lot of foundational work on large N. This is actually one of the ones I could have put on the previous transparency because there's a lot of good work both by mathematicians and physicists here, but not really in textbooks, interestingly enough. And then the other comment to make about it is that I think a lot of what one sees in ADS-CFT either it's some fusion of large N and normalization group, obviously, and so we in principle know much more about this topic than we knew 10 years ago, which hasn't been reflected in this old foundational work. So I'm not going to talk much about this one here, but I think it's another good one. Okay, so now let me get to the kind of questions that I think, why do I throw those things out as things that I would like to have? Okay, so of course the traditional question of this field is that we have these physics methods, physics results. Mathematicians would like to use them. Even physicists would like to have certain things solidly proven. I had this when I was beginning graduate school at Caltech. I had this brief number of discussions with Feynman, but in particular about the subject of theorems and rigorous work in quantum field theory. And of course, as you would imagine, he thought this was all crap, and that nothing any good had ever come out of it. And then I asked him about the CPT theorem, and he immediately, one good thing. That was the only thing. So it is the existence, theorem to show that good things can come out of this, if even Feynman agrees. And so again, there's a lot of things you could look at, but I think for the audience here in our subfield, by far the outstanding problem would be to take these many localization computations that we have in supersymmetric field theories, 2-dimensional, topological, open-closed string, Seiberg-Witten, many newer calculations in 3 dimensions, 4 dimensions, and they, on some level, even some of these are rigorous, and mathematicians write such papers, but I don't think anybody has ever written a paper starting from an actual definition of the supersymmetric field theory in question as a supersymmetric field theory, not a topological theory or something else, and showing that this is actually the answer for what we call a protected or topological quantity in that theory, and not just sort of taking a huge shortcut in the middle and saying, well, because it's supersymmetric, we only need the supersymmetric configurations. So that's surely true, but it deserves proof. And if you had a proof, well, proof number one, you'd have to define these theories. So even that's not out there. So I can confidently say that this hasn't been rigorously justified. But once you have the definition, then you can see, well, in this big integral over field space or whatever other formulation you make of the theory, here is where the supersymmetric guys sit. Here is where all the rest of the stuff is. At least implicitly, there's some sense in which it's all canceling out, or we're deforming the contour of integration, or doing something to justify this localization. And again, it's not that far. There are certainly many finite dimensional. There's 2D Yang-Mills. There's actually work by Chris Woodward and collaborators doing this kind of thing. It's not supersymmetric, but of course it localizes. And this, to my mind, is a outstanding goal. That this would show that well, yes, at least we know what quantum field theory is. We can make contact with these results that we find so interesting now. Okay, so that's an example of a question. Okay, another class of questions. Well, there are many approaches to non-perturbative QFT, both physically and mathematically, and often they involve taking limits of sending a cutoff to 0, the lattice spacing to 0, say. We truncate to some set of modes, and then consider more and more modes. And then, of course, one always says, well, as I take my cutoff to infinity or my lattice spacing to 0, this converges to the theory I'm trying to define. And then, sometimes, especially in lattice dynamic community, people make more precise statements and say, well, we see correction governed by this irrelevant operator. It vanishes at this power of epsilon and so forth. And then it kind of stops there. And there isn't really a more precise theory that's developed. And then you compare this to analogous topics where there is a mathematical theory like PDE, numerical analysis, a variety of things.
Isn't that the program of constructive field theory?
I'm getting to it. That's right.
Okay. I mean,
Except
that paragraph is sort of a description of what they're trying to do.
Well, yes and no, because the next slide is going to be something that they didn't do. So, anyways, that's right. So definitely this is a mathematical kind of preoccupation, but a very useful one to have in mind and to be able to state these claims more precisely. And for say PDE, it's been done. It's very central in the theory. And how does one do it? Well, again, it's not a huge story, but it would use up a good fraction of my talk. But a very basic foundational ingredient would be to say that we define norms on spaces of functions. So we could have L2 norm or LP norm and use those to define distances between functions. And then there's a lot of these definitions, as you'll know if you've looked at math textbooks. And then at least this is giving you a language to state these results, to say that I've approximated the function by choosing its values on the lattice. And it's true that as the lattice spacing goes to 0, that converges to the function, but only in the sense that these particular distances or these particular derived quantities converge, and then you can decide, well, for what I want to do, what kind of convergence do I actually need? And so that's a very useful tool for a thought, which is very normally part of the mathematical discussion. And so here you would like to talk about distances between quantum field theories in the same way. So if we're going to claim that we're approximating a quantum field theory, well, then we'd like to have some precise definition. Well, how close is it to the quantum field theory? And then depending on what class of theories you're looking at, you could do that in different ways. So the renormalization group is a case where this is actually kind of standard. So you're all familiar with renormalization group flow equations and the concepts, the critical surface, relevant and irrelevant operators. And so one would like to formalize that by saying, well, here's a norm on the space of actions. Here's a distance between a pair of actions. If it's an irrelevant direction, then the distance decreases under the flow. And then the better RG papers do this, starting even with Polchinski. So even physicists find themselves, brought into this mode of thinking once the question becomes precise enough. And then this is a standard part of that discussion, but not in generality, just in this case where you have an action, you have the RG, you're working by perturbation theory around the Gaussian fixed point. There really isn't any definition or any accepted definition of distances between quantum field theories constructed in any other way. And so although you're right, Jacques, that this is something that the constructive theorists implicitly talk about in their papers and books, it's not something they actually systematized. And it would be useful to do that. And so I'm working on a project of this sort. This is coming out of the paper I wrote last May. But again, this is just one approach, and this is a very foundational aspect of the discussion, which again is kind of missing to my mind, and would be useful for me and I think for other physicists as well. Okay, so then another clear sort of foundational aspect is that if you're going to show that something does not exist, and obviously you have to have a good definition and some ability to work with the defining concepts and the attributes of the thing you're trying to prove don't exist. And so one standard claim in this area, what's the simplest one? Well, there's no interacting bosonic field theory in greater or even 4 dimensions. Okay, so that's certainly something which was proven in some sense by the constructive field theorists. There's a well-cited theorem of Eisenman, and it's of course a correct rigorous theorem within the assumptions he stated. So the continuum limits of Euclidean 5-4 lattice fields, where the action has the kinetic term into 5-4, are free fields in these dimensions, and it's a fairly short and illuminating proof. But of course, it doesn't prove there's no such theory. It just proves that that way of trying to define a interacting bosonic theory doesn't work. And then, of course, if you drop unitarity and you just ask for statistical models, there's lots of theories in arbitrary dimensions. You know, you can have higher derivatives and whatever you want, and they just won't be unitary. And so once the arguments start to rely on sufficiently subtle constraints, you know, of course, you can't, you know, be sure until you have a proof that you really know what's going on. And so all that was kind of abstract, but now that we actually believe that there are interacting field theories in 6 dimensions, you know, the 2-0 theory and the 1-0 theory and so forth, well, you know, this now all bets are off there. And so you can try to cook something up using that, basically by flowing, perturbing, and so forth to get rid of the other variables. So you might take the 1-0 theory, which is the M5 ring near the Horzava-Witten boundary. So super Yang-Mills theory with matter, but now in this higher dimension. You know, it's no longer super Yang-Mills. It has a tensor multiplet and so forth. But it, in some sense, you know, it's the, you know, primordial 6-dimensional theory from which this comes. And now you can try to go out on its Higgs branch and break all the gauge symmetry. You can't add fermion masses in 6 dimensions because they are chiral, but as soon as you get down to 5 dimensions, you can add fermion masses. You can couple to the R symmetry current and add an auxiliary field and so forth. And you can get a bosonic theory, an interacting bosonic theory in the IR. Describes moduli spaces of E8 instantons. And that's in 5 and possibly 6. You know, possibly you can even do better in getting rid of the fermions in 6. So was this the counterexample to your original question? It depends what you mean by bosonic. You know, so definitely at low energies, it's got this bosons, and you've embedded it at UV completion. But of course, you know, it's got all this UV stuff, and the action, you know, the action is certainly not positive. It's not integral of a positive quantity. You know, so it certainly doesn't evade this theorem of Eisenman specifically, but it's sort of in between case. You know, there are things to say about these theories in higher dimensions. Okay, and then let me go quickly over this one because I've given talks about it. So once you can show that some quantum field theory doesn't exist, then you can start making general statements about the space of the ones that do. It's really, there are good reasons to think you'll never classify it except for special cases, but that's obviously an important question. What can you say about it? One important and well-studied goal is to define the central charge in every dimension which decreases under RG flow. Once you have that type of measure of the number of degrees of freedom, you like some sort of statement that the set of the conformal field theories with that central charge from below is finite in some sense. And the right way to say that is pre-compact, and you have to put a lower bound on the operator dimensions. And this has been discussed in my other work. And then once you have such a well-defined set in your hands, you know, what class of construction suffices to make it. So at least in 2 dimensions, you can't prove, there's no clear argument that you can't do them all by linear sigma models, gauge linear sigma models of various types. I don't know that's the case, but it's still at this point a valid, you know, a plausible conjecture. Okay, so those were questions. Now let me quickly survey some of these approaches. And of course, the first thing that we would go through if I were trying to, you know, spell all this out is that different approaches talk about different data. You know, they might talk about correlation functions. They might just construct operators. They might talk about the S matrix. Once you have these things, again, defined precisely, there's a lot of math you can call on that really helps you out. And in fact, the relation, certainly between the first and the third in this constructive field theory literature is almost trivial in the sense that you put the right axioms. I'll skip ahead. I'm not going to list the axioms, but if you put the right axioms on the data, so these are appropriate axioms for correlation functions with certain growth or regularity conditions. These are appropriate axioms for this operator Hilbert space formulation. And once you have them, there's sort of, you know, simple universal constructions where you can take all the correlation functions and get an operator algebra and representation that actually realizes that, you know, and vice versa. Since you've said the properties that the things have to have in order to make those relations work. And so that's part of the, I mean, that's you know, certainly real content in this, you know, axiomatic quantum field theory beyond the CPT theorem. Of course, it's not observable content, but it certainly shows that these are equivalent ways of talking about the same thing. But then there are many other ways of talking about the same thing developed since this time, which are, we don't have these equivalence theorems, such as conformal field theory, the BPZ, the 3-point, the OPE coefficients and operator dimensions. Again, we know, BPZ told us that determines a two-dimensional conformal field theory. In principle, in arbitrary dimensions, that's true. Can you prove, that it really determines this other data? That would certainly be worth knowing. If you have all the partition functions and all genus surfaces, can you prove that determines the rest? Well, again, so okay, so then, well, these explicit or rigorous approaches, certainly the explicit construction in terms of some explicit operator algebras, the ideal case, and well, the free field theory, is one where you can certainly do that, and one tends to, familiarity, breeds contempt, but there are still good questions about free theory, especially if you put it in a curved background. Questions about how modular invariance works on the torus, how different, how this responds to the metric. Again, there are questions that have been asked, but not all the answers that I've wanted in my work thinking about other theories are out there, and this is certainly rigorously defined. Okay, well, of course, there are rational conformal field theories where we can write down operator algebras in terms of Kac-Moody algebras and the rest. And again, this is touching on topics I've spoken about, the paper I wrote a year ago and so forth. To what extent can you think of a conformal field theory as a sigma model, or perhaps a Landé-Ginzburg theory with a target space and a potential, and then compare to the analogous geometric things. In other words, quantum mechanics with that target space and potential. And again, we've focused very much on the differences, and there are, that's in some ways the most important thing, but it's the similarities in a way that are equally striking, that you can think of WZW models as strings on a group manifold, and you can basically think of the state spaces starting with quantum mechanics, adding the string oscillators, and then reducing it by this RG flow. And not everything, but a good deal can be understood that way. And it's a project I've been working on to try to ask the same questions for orbifolds and Gepner models, that the C is the same in the large volume limit as in this stringy regime. And there has to be some map between the states of a sigma model with a Calabi-Yau target in the large volume limit, in the small volume limit, on the orbifold, and so forth. And again, one has this picture. In the large volume limit, one has L0 plus L0 bar contains the Laplacian momentum states. It contains winding states, contains oscillator states, and you can geometrically see where they come from. But for example, there isn't actually any proper discussion of this winding state contribution in the large volume. These are very high dimension operators, but they're there. And what's the alpha prime correction to a winding state beyond the length? Well, nobody worked that out. And if one can understand this formula, I have the suspicion that a Gepner model not only is a analytic continuation from a large volume Calabi-Yau, but you'll be able to look at terms in its partition function and match them up in some way. But we don't even have the large volume thing to match them with yet. Okay, so this is getting into this question about perturbation theory around other solvable theories now. So suppose you understood the Gepner model, there's this region around it in the moduli space of superconformal field theories that you could access by perturbation theory. The observables, we believe, are analytic in those coupling constants, so there's no reason that perturbation theory couldn't be convergent. You set up like the torus case, and it is convergent, so why not? And again, this kind of basic foundational thing that was never worked out. So it'd be nice to have. Okay, so let me briefly survey a few other things and then talk a bit about constructive theory and then end. So of course there's been important developments in mathematics and even 2 recent Fields medals for proving that particular 2D theories exist rigorously. So this is generally taking the attitude that you have a lattice definition like the 2D Ising model or percolation. And of course, that's a rigorous thing as it stands. Just you'd like to take a limit of it, or show that certain quantities, say, have a zero lattice spacing limit. And very, very pretty, novel, concepts show how to think about those things in the continuum limit. So this famous Schramm-Loevner evolution that describes various contours, random contours that arise in these models. So there's a percolation boundary, the boundary around a percolating region. You can prove that it is a random curve of SLE. Smirnov has proven that a number of lattice theories are conformal in the limit without the brute force approach of computing all the correlation functions and taking their limits. He actually has a formalism that lets him say that, well, here's the free fermion operator over the Ising model. We've known for, 60 years what it is, but does it become an actual conformal field theory fermion in the continuum limit? Is it really a holomorphic function on the world sheet with the specified cuts and so forth? And so you can define a discrete holomorphic function on the lattice and set your definitions up so that the lattice fermion is a discrete holomorphic function, which is not the same. It doesn't obviously go over to a continuum holomorphic function, but it's certainly in the ballpark. And this facilitates getting the control over the theory to show that, well, yes, it does go over to a holomorphic function. So there's a lot of interesting developments to learn from there. Let me now talk about this constructive theory. And there, the basic observation goes back to Dyson and the fact that standard perturbation theory, and the coupling constant around free theory is only asymptotic. The G loop grows as G factorial, has zero radius of convergence. There's very good reasons. In fact, the actual answers are not analytic at zero, except in some wedge. So that's inevitable in some sense. So you can't sum up the series. How do you work with a theory? How do you know it exists? So that was the traditional problem of this constructive quantum field theory, and they came up with a solution, which is called the cluster expansion. And I'll briefly explain the idea. So where the problem comes from is the large field regime. So here's a zero-dimensional integral over a single real variable phi for phi-4 theory, and it has an asymptotic expansion, just like field theory. But there's something wrong here because the integral, the interaction term, which seems to be making the expansion so badly behaved, actually makes the integrand converge much better than the free theory. Just the problem is it does this if lambda is positive, and it doesn't do it if lambda is negative. So it's this non-analyticity that leads to the problem. And then there's a kind of brute force way to fix it, which is to say that suppose you cut up this integral over R into three pieces. You have some big number C. You got the middle. You got the ends. And you can easily check, go home and do it, that the integral bounded up and below by C, that series expansion, you get a convergent series expansion, because obviously the terms are bounded above by this e to the minus lambda C4 thing. And so that's grows as a power of C. Phi to the 4n grows as C to the 4n. That's actually convergent. And then because you've got this e to the minus lambda phi 4, these other tails give this tiny correction, which goes away, and you finally take a limit. And so it's a little brute force, but it certainly works. The problem is that now you have to do it in field theory, and you have both these interaction terms at every point, but you have a kinetic term which couples neighboring points, and it's only simple in momentum space. And so now you've got two different things going on. And so then what they do is they say, well, let's set up the usual perturbation expansion. We know how to do that. We know how to renormalize. But now let's overlay on that some sort of a decomposition of position space into a lattice in the sense that we've cut it up into some collection of hypercubes. So the cells of a lattice. And then within each of those hypercubes, we're going to do this kind of decomposition of the integration over the field. And so wherever we see the field getting large, we now apply this argument that says that, well, actually the interaction is just totally killing that contribution. And then this works, actually. This is the technique that was used to construct polynomial interactions in 2 dimensions, the phi-4 theory in 3 dimensions. So there's definitely, content. In some sense, they solved, a problem of value to us. The problems with it are that it's a real mess. This expansion. If you get into the details, and you can kind of see from what you're doing that it is a mess, and it doesn't fit too well with gauge. Gauge symmetry you can do by going back to the lattice and doing lattice gauge theory. Supersymmetry is hard to reconcile with this thing, but actually not impossible. Okay, so here's a little bit more detail about this d equals 2 case. So this is the case where there is something to prove, but it's not a very hard thing to prove. So you have to normalize the interaction. You have to normal order. So you think about a Landau-Ginzburg theory with just some number of bosons and a potential. Sometimes you have to normal order the interaction. And then the subtle problem is that if you actually think of this at finite cutoff epsilon as a function of phi, you can actually check that these low order terms, they go as log epsilon and log squared epsilon, and you get this tiny region of field space where the potential becomes arbitrarily negative because of these renormalization, these subtractions. And so the potential is actually unbounded below, but it's unbounded below on this very, very tiny piece of field space, and you can show that the kinetic term and so forth keeps you out of there, and it gives you a finite theory. And so that was the content of this discussion. And again, there's a variety of interesting things that were done in this way. Now, I think you can use this for supersymmetric theories, not in great generality, but in this this lattice supersymmetry formulation of Catterall, Kaplan, Unzel, and others, where basically you take the theories, supersymmetric gauge theories, some others, where you can twist a theory so that you no longer really have fermions. What you have is a Dirac-Kähler fermions, which means differential forms on the lattice. Okay, so if you're in d dimensions, then of course if you list all the forms, they have 2 to d components, the collection of all forms from 0 up to d. And if you have that many fermions in your theory, then there will be a twisting for which the fermions combine, embedding in the R symmetry and the Lorentz Euclidean symmetry, become these forms. So you get the A-twisted 2, 2 theory that's got 4 fermions in a multiplet. And you can actually get n equals 4 super Yang-Mills that way. And then what you can do is you can exactly realize one nilpotent supercharge. Right? Of course, you can't get real supersymmetry on the lattice, but you can get a single nilpotent supercharge on the lattice. And so they were kind of happy with this because at least it's something you can use to control the theory when you numerically simulate it. And of course, we can be even happier with this because after this initial part of the discussion, we rapidly choose one nilpotent supercharge and tend to concentrate very much on that topological sector of the theory. And this is saying that some of those theories really can be embedded in lattice theories that should be constructible, this 2-dimensional case constructible more or less using the techniques already developed by Glimm and Jaffe and others. So that problem of justifying localization that I started with really doesn't seem like a crazy problem to work on. It seems like the ingredients are there. I was looking at this with A.J. Toland, one of our postdocs, and we got a certain distance, but it turns out that there's this subtle point that we eventually realized that stopped us, or at least it means that you do need something new. So what you can try to do is you can take the A model and do these instanton calculations of a gauge linear sigma model where you integrate over vortex moduli spaces. So some of you will know this. I think Sheldon's talk referred to a bit of this. There's, say, U1 gauge theory. There's, chiral supermultiplet Z, and then there's some, potential in a defining function, P of Z equals 0. And the instanton is a holomorphic map from the worldsheet into Z, satisfying this nonlinear equation P of Z equals 0. And then it turns out it's exactly the same discrete holomorphic function that Smirnov was using. So it's not a new concept, and quite a bit is known about it. And one of the things that's known is that when you multiply 2 discrete holomorphic functions, it's not discrete holomorphic anymore. Okay, so it's got this little, del bar non-zero piece. And so this now becomes a hard equation to solve. You can't just multiply, z equals, little z and so forth. And that's kind of as far as we got. And then there are reasons, actually, if you know about this stuff, it shouldn't, the instant-time moduli space has these subtleties, and it shouldn't have been too easy to do this, but we have ideas how to proceed at this point. In any case, you can certainly set up the problem that I discussed. Okay, so let me just make a couple more words of comment. Okay, so so much effort to make these constructions work, to get a conversion to expansion, but again, it's a problem which is intrinsic to the situation. Weak coupling, perturbation theory. There's really even physical reasons why the loop orders grow factorially. And even if you totally reorganize the perturbation theory, say our friends who work on n=4 gauge theory find this incredibly simple twistor formulation which allows you to write down every amplitude in a few lines to all loop orders. Well, I bet they will still grow as as L factorial at L loops, right? Because it's physics that makes them do that, not some sort of deficiency of Feynman diagrams. And so then they will face this problem. And so it's a problem worth thinking about at this point. And I think if a little presumptuous, but I think this cluster expansion, it works, and the main criticism you can make of it is kind of ugly and complicated. And on the other hand, the idea in itself was fairly natural, is to say there really is this large field region where the fields become large, and we just have to treat that differently than the small field region. And it's kind of a mess, but so was perturbative normalization when people first started working on it. There's this large momentum region and the order 1 and small momentum region, and you just have to treat them differently, and you have to do special things to isolate the contributions of the large momentum region and use them to renormalize the couplings and so forth. And so the fact that people worked on this problem for 50 years and cleaned it all up and found the beautiful structure in it is why we can be relatively happy with this. And trying to now either make this type of decomposition of configuration space or something else that has the same effect in a more geometric way, in a way that allows at least, if you have messy choices to make, you at least like a formalism that makes that relatively simple to work with. You've isolated the messy choice. If you change the messy choice, that's some sort of natural covariance or homotopy of your formulation. And so it may be that this is really a valid way to go, but it just has not received the sort of technical and mathematical attention that it should, and it could be made prettier if one did that. So I'll stop there.
So you talked about, for instance, trying to improve localization formulas and things like English for Cipriano that, for instance, involves defining such a theory. And of course, we don't really have, arguably, we're pretty far from being able to define, to that level of the required level of precision, non-Abelian gauge theories, even non-supersymmetric ones. I mean,
that's right. That's why I would certainly encourage people to work on the two-dimensional problem.
If not, let's thank Mike.